So welcome to PTV Talks. We're going to go over some tooltips with Viswalk today. And the two main things that we're going to be talking about today are attribute modifications, which are a new feature in Vism 2021, as well as nearest neighbor pedestrian attributes, which are both attributes of the pedestrians in the network as well as some evaluations that we can look at, and then how we can use those to look at some new ways or old ways of modeling in Viswalk. So quick introduction of myself. My name's Levi. I'm the training manager. I've been at PTV for about coming up on 7 years actually, and I started as the Viswalk modeling specialist way back in 2014. And so, yeah, today we're going to start by talking about attribute modifications and what are attribute modifications in Vism, in Viswalk. So traditionally, the role of COM in Viswalk is to augment some of the calculations that are inbuilt in the software. So you could do things like collect network information where you can read data out of the network, and then you'd have a Python script or a C++ script or something like that, perform some custom calculations, and then you would read back data into the network file and update various Viswalk attributes. People would do things in COM to help with routing or dwell times or lane closures for security terminals or something like that. But now we can use attribute modifications within Viswalk to do some of those calculations. They don't have full access like COM does, but you can do some things. So for example, on the collect network information, you can use lookup tables. You can access some of the attributes directly, and then you can do all of the typical formulas or functions that you would see in a formula-based route or a formula-based user-defined attribute. So if then functions and the attribute modifications work kind of like a for loop. So you would say, it would cycle through all the pedestrians in the network and apply some filters, and it would say, okay, all pedestrians that are of a certain type, I want to edit this attribute, or all pedestrians on certain areas, I'd want to edit a specific attribute. Or you can use attribute modifications on network objects like areas or ramps or obstacles or links or something like that. And then within the attribute modification, you can, again, put in some custom calculations. If functions, logs, rounding, you can modulate, you can find the modulus, you can find the root, etc. And then you would write that back into existing attribute values, or you compare it with formula-based routes or user-defined attributes as well. So quick look at the attribute modification setup. This is going to be in the actions menu. So up at the top of your Viswalk, there will be next to the help menu, there is now an actions menu instead of a scripts menu. And that's where your event-based scripts are, and that's where you'll see an option for attribute modifications. And we'll look at VSIM more specifically later on down the road. But in the setup for an attribute modification, we have some key areas that we have to look at first, so you kind of have an idea of what attribute modifications can do. The first thing we're going to see is the modification name up in the upper right. This is just a custom name that you'll define for this specific action. And an attribute modification is one action that you can perform. And a way I like to think about it is, if this is something that you could do, for example, manually during the simulation, right? So you could pause the simulation and perform an action on a pedestrian, change their speed, count them, something like that. And so this is you'll define the action, and then you need to define when you want it to execute. So that will involve the simulation from and to time, as well as the update frequency. So when do you want it you want this attribute modification to happen. Maybe you have a warm-up period, or there is, you're running 2 or 3 hours of simulation and you only want this to be active during the peak period or something like that, during the rush. And then you have to define the object being updated. So you can, the object types are various. So you can do links, vehicles, pedestrians, areas, ramps, all of the physical objects in the network editor you can access, and then some extra objects on the side, like evaluation tools. We'll see that you can do area measurements or data collection measurements as well. And then finally, you'll have to specify what is the attribute being updated. So in this example, we're looking at the desired speed factor of a pedestrian. In this case, the desired speed factor is a multiplier where you can essentially set it to 0, for example, to stop the pedestrian, set it to 1 to have them move at normal speed. Anything over 1, they'll move faster. And anything between 0 and 1, they'll move in between. Then down below this first box, we'll specify the object filter. So this will look for only pedestrians, in this case with the number 1. Alternatively, you can filter by pedestrian type or what area they're on, or sorry, this is object. The object type is area number 1. So this is only looking for area number 1. And then finally, at the very, very bottom, that's where we specify what is the action we are performing. What is the user-defined formula? So basically, this is saying for area number 1, we want to count the PEDs. And if the PED count is greater than 100, then we will assign the desired speed factor to 0. Otherwise, we'll leave it to 1. The way I like to read this is you just kind of start by reading the time, and then you'll kind of move down sequentially. So for example, in this example, we'll read this as during the last 10 seconds of the simulation, and we can see 5990 to max, which is a 6,000 second simulation. And then we'll run every 20 time steps, which in this case is every 1 second. It will basically, at the beginning of the time step, we want to look at area 143 and look up the risk value attribute, and then identify all the area measurements with the ID number 4. And then for each of those, we will assign it a value called nearest neighbor risk value in store. So Adam Groves, I'm going to pass it over to him. He has a couple examples about how to use attribute modifications for various things, like pickup drop off, as well as a holding lot example. So Adam, take it away.
All right, thank you, Levi. I'll just make myself presenter here. All right, so Levi, can you see my screen okay?
Yeah, I can see your screen.
Perfect. Okay, so as far as Viswalk goes, a lot of times we see people using Viswalk in the context of pickup and drop-off operations. It's one of the most kind of commonly used things, and we get a lot of questions about it. So I'm going to walk through just a couple examples that show you some ways you can implement some of those features. In this first example, we have a pretty simple area here where we have a couple parking spaces where vehicles are going to come either pick up or drop off passengers. Only limited spacing, so you can imagine this in terms of an airport or something like this. And then back here, we have a queue that will form that will hold excess vehicles that can't make their way to this parking area when there's no availability. So we're using that with a stop sign. Basically, that stop sign is set to have like an arbitrarily long wait time so that none of the vehicles will go through the stop sign until we tell them to, basically. So this simulates something like a holding lot for rideshare vehicles or taxi rank type operations or many of those types of things. So what I'll show you a quick example. So I'll go ahead and start the simulation. And what will happen is vehicles will start to come in from the left, and the first couple will just stop briefly and release and make their way over to this parking lot. And then they will dwell for a minute while they would either be picking up or dropping off passengers. And as soon as they leave, you will see a vehicle get discharged from the stop sign pretty much immediately. So previously, this was, as Levi kind of mentioned, difficult to do, and maybe you wouldn't do this without COM scripting. So I'll show you that can be accomplished with just one attribute modification here, and we'll dive in a little bit to the details. So in this case, we have a attribute modification that's running every 10 time steps, so basically once a second, and it is operating on vehicles in the network, because ultimately the item or the attribute that we want to change is the dwell time of the vehicle. So when the vehicle stops at the stop sign, it's assigned a dwell time, and then that counts down every time step until it's time to be reaches 0 and it's time to be released. So in this case, basically what we're going to look for is a couple things. So the only vehicle we want to modify is the first vehicle in line, and we only want to modify it when the parking lot has availability. So the first item we're doing here, the first filter, is we're checking the length of the stop sign on and looking for the vehicle that's furthest along that link. So the vehicle's closest to that stop sign and is equal to the position of the vehicle we want to modify. So basically that just makes sure that we only modify that first vehicle in the queue. The second thing we want to do is only do this when this parking lot has availability. That's done through the current availability feature on the parking lot. So that takes into account both if there is a vehicle in every parking space, but also any vehicles that is already booked a spot on that parking lot. So as soon as a vehicle enters this parking decision, then it will be counted in the availability. So that way we won't have vehicles get released prior to them actually making it to the parking spot. And then simply all we're doing here is we've chosen dwell time as the attribute that we want to change, and we're setting it to 0. So pretty straightforward way to get that kind of taxi rank or holding lot. You can also do something similar to this with parking lots as well. So if rather than having this kind of taxi rank type operation, you can also do this with a parking lot. The dwell time attribute is what also releases those vehicles from the parking lot. So you can change that based on, for example, looking up which vehicle has been in that parking lot the longest. So the first one to give you that kind of first come, first serve operation. So, and that's all there is to it for that. And I will go ahead and show off another example that actually comes with the software too. So this next example was recently added, so you may not be aware. If you don't know, you can always access the example files by going to Help, Examples. In this case, it's under Training Directory. And then it is under the Pickup Drop-Off and Courier Service. So I'll switch over to that example file now. Now, in the default example file, this is used by uses packages, but in this case, I've modified it to use pedestrians. And basically what we have here is this kind of circular network. At each corner of that network is a place where people are either going to be picked up or dropped off. And we have this kind of holding lot here that's used to store vehicles while they don't have any assigned pickup or drop off operations. And then in this view here, we just have a few, a 2D and a 3D view. So hopefully this comes through okay over the web. Sometimes these animations aren't the best. So basically, as the network loads, it seems to be running kind of slow. Vehicles will enter the network. Currently, if they don't have any assigned operations, they'll go to this holding lot, and I will zoom in as people come in. As pedestrians enter this network, vehicles are dispatched to serve those requests. They'll be picked up and transported to whatever terminal their destination is. So as we watch this, you'll see in this case, a pickup happen and periodically be drop-offs too. So I want to call your attention to in that same directory where the example file is. There's a really good description of how this works. There are a couple small COM scripts that are still required in this case, primarily around that drop off as well as dispatching those vehicles. But there's a really detailed example. And the good thing about this is as well that script and all the attribute modifications included, which I have pulled up here. I think there's about 13 of them, are designed in a way that these can be easily transferred to other models. So if you find yourself, you can see how this would be used in context of maybe autonomous shuttles or, some kind of pickup drop-off operations, even like inside an airport with small like autonomous vehicles, things like that. So it takes a little bit going through that PDF file and understand the description. But once you understand this can be easily expanded and applied to other models. So we just wanted you to be aware that this new example file exists, and it can be easily applied to other models you may have. And with that, I will turn back over to you, Levi.
Thanks, Adam. Let me just start sharing my screen again. So with the attribute modifications, again, these are often things that you would have to do with a script that now you can do directly within Vism. So some of the things that we're also testing out with that pickup drop off is putting in calls for cars and things like that, like he showed with that particular example. And so it's not necessarily Viswalk specific, but we have a lot of people asking about pickup drop off with Viswalk as well. So all right, the next thing we're going to do is we're going to start talking about now the new attribute called the nearest neighbor in Vism, in Viswalk. And in Viswalk, the nearest neighbor is an automatic calculation that it does where basically it will identify which pedestrian is nearest to each target pedestrian that you look at. So if you look at pedestrian number 1, it will look around there or around that pedestrian number 1 and identify which person is closest to them. So there are 3 main attributes in the pedestrians in network. There are 2 main attributes, sorry. There's the nearest neighbor pedestrian ID, and then there is the nearest neighbor distance that you can pull up. So it will identify which pedestrian is closest, as well as identifying that pedestrian number. Now you also have the sub-attribute selection where you can pull information from that. You can pull all the pedestrian attributes from that nearest neighbor. So what their speed is, what their pedestrian type is, what their route number is, things like that. And so that nearest neighbor will allow us to access pedestrians around us. One thing to note is that the nearest neighbor will see all pedestrians as long as they're on the same level, and they'll even look through obstacles. So that's something to be careful of if you are looking at the nearest neighbor calculation and you have somebody on the other side of a wall. They might pick up, and you want them to identify somebody within the room. They might pick up somebody on the other side of the wall, so you'll have to be careful about that. But that's where you might filter using an area number, the current area number, rather than just explicit distances. So the example we're going to be looking at, which is quite poignant in today, is an example of social distancing and how we can analyze that within Viswalk. And so we're going to be using this nearest neighbor attribute to do that. And so again, the key thing that we're going to be looking at is that nearest neighbor distance. Some other things we can do is pull out area results for the average nearest neighbor distance, the maximum nearest neighbor distance, and the minimum nearest neighbor distance. So you can for different time intervals. So you can actually pull this out as in the pedestrian record as well as on the area results. And so if you're looking at something like a platform, you can look at the average distance between people on the platform and kind of get an idea of how spaced out people are. Often we look at density for something like that, but this is the nearest neighbor result is a lot more tangible for people who aren't in the know about, what does pedestrian density mean and things like that. So it's a lot better for, sharing with stakeholders as a form of a result. The average distance between people is say 2 meters as opposed to, X number of pedestrians per square foot or something like that. Currently, though, it's not available for the grid cells, so you can do the area results visualization, but it'll color the area as one color rather than splitting it up in different grids. So, but that's on the development to-do list. So, talking about color schemes real quick, we can add color schemes to the network both on the pedestrians, and we're going to be seeing this in the upcoming file, where, for example, we can create a color scheme based on social distancing, and this is in meters, but where we have, an unacceptable social distance is less than 1.5 meters, right? So anyone that is within 1.5 meters of another person, they are colored as red. Anyone who is within 2 meters is colored as yellow because they're getting kind of too close to people. And then anything outside of that, they're just given their normal color to show that they are at an acceptable distance. And then similarly, we can do the color scheme, a similar color scheme for pedestrian area results. We might do a more gradient version if you want to get, a larger scale of colors or a larger color scheme. Or you can create the same color scheme that you'd use on the pedestrians for something like social distancing. So moving, how can we use our nearest neighbor? And that's where we're going to start talking about something like capacity modeling. So currently in pedestrian modeling, people are looking at things like fire safety, and we always create fire safety evacuation plans and earthquake plans and things like that. But something that's been in discussions more recently is, okay, how can we deal with, reduced capacity for other reasons, right? So how can we better create policies and things like that around, something like a pandemic or contagion that's going around. So in that case, before I get too far into this model, I just want to make a couple quick notes about this. The model that we're going to be looking at is a supermarket model, and we're going to be talking about things like social distancing and stuff like that. But this by no means it means that Viswalk or PTV Group has done any extensive research on transmission rates or anything like that of any illnesses or anything like that. So this model will not contain any of that. We're just going to be looking specifically at how much time are people spent within a certain proximity of each other. And then you can do what you will with that information. But we aren't doing any sort of calculations on transmission rates or anything like that. The key here is that we're going to be just using we're going to be using this as a surface level comparative analysis to see, okay, what kind of operational strategies can we implement that will both optimize our capacity of our facility while minimizing, the risk that people are taking while using our facilities, right? So we're going to be looking at something called nearest neighbor risk value, which is just talking about how much time have people spent within a certain proximity of each other. We're going to be using 1.5 meters as the minimum distance, and then 2 meters as a kind of boundary condition. Okay, so there are a few things that will be added to this model to make our nearest neighbor calculations work and things, or not our nearest neighbor, sorry, our risk calculations work, right? So we're going to be looking at a supermarket model, and we're going to be analyzing how are people doing within proximity to each other? How is our volume to capacity ratio looking? And so we're going to be creating a couple user-defined attributes. One is for body temperature, because at this particular model, there was a for this facility, there was a temperature check at the door, and then an exterior line where people would wait if it was over capacity. The other thing that we put in as a UDA is this risk value assessment factor, where basically if they were within a certain if they were within 2 meters of each other, then the closer they got to that person, the higher this risk factor would be. So basically, it's a formula-based user-defined attribute where if the nearest neighbor was within 2 meters, we applied a risk factor that scaled up as they got closer. Some area UDAs that we created to help with this model. So these are user-defined attributes on the specific areas or the floors. So we have an area outside where people are waiting in line, and then we have the actual supermarket floor as well as an area. We created a few UDAs. I'm not going to go through all these in great detail, but things like user-defined attribute that counts the number of pedestrians, as well as the room volume and things like that. We also have a few attributes that store data, like we're going to be using attribute modifications to count how long people have been within 2 meters of each other. And so we have a distance violation seconds user-defined attribute that will store that total amount of time people spent in the store within 2 meters of each other. This model also has a decaying rate for diffusion. So as you walk through a space with an open air space, there are going to be different diffusion rates and things like that. And so we applied a few of those decaying functions in there as well, so that way that the overall time will decay a little bit. And then finally, the nearest neighbor risk value total. So this will look at all the pedestrians, and it will sum up those aggregated risk values that we saw in the user-defined attribute previously. And then finally, we have some user-defined attributes at the area measurement level. And the reason we have these at the area measurement level, not at the area level, is because you might have some spaces that are made up of multiple areas. And so you can group together those areas as area measurements. So for example, if you're looking at an airport terminal, right, you might have one area for the whole security terminal, or you might have one area for security terminals A and B and another one for C and D, and then you want to group together all security into one large security terminal analysis. And that's how you'd use an area measurement. It's kind of like a data collection point versus data collection measurements, where you might have 3 data collection points across 3 lanes, and you group them together for a link analysis, right? So you do the same thing with an area measurement. So we created a couple area measurement user-defined attributes to, again, store data, like what is the total risk value outside versus the total risk value inside, and things like that. Time spent in store. And all of these are going to be calculated using attribute modifications. Okay. Now we're going to get into the actual attribute modifications that we created in this model. I'm going to introduce them. I'm not going to go through all of them in great detail until I get into the model itself, so you can kind of see what they look like. But here's just a little bit of an introduction on them. We're going to have 3 different types of attribute modifications. We're going to have a group here that I'm showing now are types of attribute modifications that are triggered at the beginning of the simulation. And basically their whole purpose is just to reset all of these values, these aggregated values. So as the simulation goes on, it's going to be recording things like time spent in the store and things like that. And we're going to need to reset all that to 0 at the beginning of every simulation. So you can either manually do that, go through all of the areas in the network and just reset their values, or you can quickly create an attribute modification, which is, again, just like a for loop. And you can say for all areas in the network, reset the total time pedestrians spent on the area to 0 kind of thing. And so that's a real quick way to initialize your simulation. And so we'll have 5 of those that do that. And then we'll have a few more attribute modifications during the simulation that are computing different things. So the first thing is we need to identify how much time is spent within that minimum distance of 2 meters. And so you'll see here, it's just it's kind of like a counter in a com script where you'd say, the counter is equal to the counter plus 1, right? Here, we're going to be running the simulation with 20 time steps per second. So every 10th of a second, or every 20th of a second, we need to add 1/20th of a distance violation time. And so that's what that 0.05 is. And then so we'll calculate the distance violation time. We'll compute the total time spent on an area. We'll compute, every time a pedestrian is on an area, we'll add a 20th of a second. And then we'll take that pedestrian time and we will apply a decaying factor to it. So we can look at, okay, what's the difference between, the total time spent by pedestrians versus if we had some sort of decay rate and we created an arbitrary decay rate. And then on top of that, we took it a step further and wanted to give you an example of what happens if we have a decay rate that's based on the volume of the space, right? And so we have one that's based on the current density of the pedestrians versus the size of the space. And then finally, we have one that's computing the nearest neighbor risk value. So as pedestrians accumulate that risk value, we're going to be adding that to the total of the respective area, either inside the store or outside of the store. And then finally, we have some attribute modifications that we're going to be using that will be logging this information. So we don't want this information to just disappear at the end of the simulation, or maybe we want to look at time-specific intervals. So on the most of these are going to be on the area measurements, because the area measurements have those time intervals associated with them in the evaluation configuration. So you will be storing data at various time intervals, looking at distance violations, the total seconds in the store, the total seconds outside, the total time spent in the store, our decay, and our risk rate. So here's what the workflow is going to kind of look like, just so you kind of have a roadmap of where we're going to go. The first thing that's going to happen is that Viswalk is going to pull that nearest neighbor information. So it's going to look at each individual pedestrian. It's going to say, okay, who is closest to that pedestrian? And it's going to analyze, okay, it's going to break that off into 2 tracks. The first track is going to be, okay, with that nearest neighbor information, we're going to, at the pedestrian level, analyze the risk that individual pedestrian is experiencing right now. So if we look at these 3 pedestrians in the queue, that first pedestrian is within 1.5 meters, and so they are accumulating a lot of risk because they are really close to other people. Whereas the person that is yellow is within 2 meters of the person in front of them, so they're accumulating risk but at a lower rate. And then the person in white is outside of that 2-meter boundary, and so they are accumulating no risk. And then finally, we have an attribute modification that will sum up that risk that is accrued as people traverse through the various aisles in the store. The other track that we're going to be looking at is so this is at the pedestrian level, at the pedestrian risk level. The other thing we're going to be looking at is the time spent within that social distance. So it's going to take that nearest neighbor calculation, and it's going to pull that information out. And every time step that this person is within, this yellow person is within 2 meters, they're going to be adding to that time. And so the attribute modification is going to be adding that to the store total time. And then we can apply a decaying factor, and then we can look at the total number of pedestrians that were affected within the store, in terms of this is the total number of pedestrians that would have been within that nearest neighbor distance, with a little bit of decay applied to it. So those are the two main workflows that we're going to look at. So now we're going to actually jump into the Viswalk model. And so I have two separate models here that look virtually the same, but the key difference between these two models is in the second model, we have configuration D, where the pedestrians are only able to walk one way up the aisles. So they can, they're not allowed to, there's a explicit path that they have to take. Whereas in this configuration E, we have them kind of randomly walking around, checking different aisles and going to different aisles and passing by each other within these narrow aisles. And the key here is that we can use this as our comparative analysis. Again, we're not doing any sort of transmission rate analysis or anything like that. That's not to say that you can't do it. It's just we haven't done any studies on it. So that would all have to be done based on your own research on that. PTV doesn't provide any sort of information on that. That's something where you'll have to check peer-reviewed journals and things like that for that type of information. But here we can see, just at a comparative analysis level, real quick, the two different simulations. And if we compare them side by side real quick, so let me just do this. So that way you can kind of see what's going on. You can see here, again, the one on the left, people could randomly go up any aisle they want. And then on the right, we instituted a more strict pathing scheme where you can only go a certain direction up each aisle. And you can notice that from a capacity perspective, even though configuration E pumps more people through the building, we have the same number of pedestrians in both models. And this one had completed all the pedestrians in the queue. But you can see that the distance violation time in the store was 9,000 seconds total, whereas with this configuration, we didn't quite get through all the pedestrians. There's still a little bit of a queue, but the distance violation time in the store was only 650 seconds. So that means that only 657 seconds was spent within that minimum distance of each other, as opposed to 9,000 seconds. So here are some ways that we could use this nearest neighbor and the attribute modifications to do comparative analysis to plan out different mitigation strategies, right? Now the downside to this is that if we look outside, people spent more time outside. Now, it's bigger, it's open air, so if we looked at the airflow of the space, it might not necessarily matter quite as much. So those are some things to consider as well when doing this comparative analysis, is how much time are people spending in each location, because if you limit the capacity in one space, those people are going to have to go somewhere else. But this is a good way to look at, okay, maybe you're comparing, you're at an airport, for example, and you have a certain strategy for different peak hours, for using different security terminals, numbers of security terminals. And then you can institute various tests where you can look at how many security terminals will it take to what is the optimal number of security terminals you can take to minimize dwell time, as well as risk to your customers. So let's look at this one in particular, since it still has pedestrians running. I'm just going to hit play on the simulation so we can kind of see as pedestrians are kind of making their way through the store. They're moving forward, and you can see that they'll blink red as they step within that space. So here's a situation where maybe this temperature check is actually causing a hazard outside, because as they progress through towards that body temperature check, they're actually getting too close to the person in front of them or behind them. And then here we see things like corners and stuff like that, where commonly people are still getting into trouble because these aisles are a little too skinny on the sides. Let's take a look real quick at the attribute modifications themselves. So I'm going to pause the simulation. Attribute modifications, again, can be found in the actions menu and under attribute modifications. And then here in this list, we can see all the attribute modifications that we talked about before. We have the 5 initialization ones. And so this is just a pretty straightforward. You look at a specific attribute and you set it to 0. And here we have it just execution type before the simulation starts. So what that means is when you hit play after initialization before the first time step. So this will automatically set this attribute to 0, which is the distance violation in seconds. And then we have 5 of those that all initialize, and they're all the same kind of in that sense. And then we have an attribute modification here, or these next ones compute during the simulation, so we can see that they're running during the entire simulation at the start of each time step. So when the clock rolls over to the new time frame, it first calculates this before the pedestrians move. So what we're looking at here is we want to compute the distance violation. So we want to count how many people are within 2 meters of each other. So if we look at our model here, what this is going to do is every 20th of a second, it's going to count each one of these people and add a 1/20th to the total, because they're all within that 2 meters of each other. We don't want to do that for all areas, so we're going to be looking at 2 specific areas, area number 2 and area number 143. And area number 2 is this outer area here where the queue is, and area 143 is this inner area inside the store. So what we can do is we can filter, and here we're using an OR function, and you can see that here in the operators. We have this OR function, so it says, okay, if it's going to look at all areas, and if that area is area number 2 or area number 43, then perform this calculation, which in this case takes the attribute value, the distance violation in seconds, and it adds the current violation total multiplied by the 0.05. And you can access various attributes using this attribute operand right here. And these are all the attributes of the area that you can select. So these are all physical attributes, evaluation attributes, or user-defined attributes that you can grab. You can also use a lookup table. Oh, I accidentally added an attribute here. Don't want to do that. There we go. You can also use a lookup table to pull attributes from other object types. So if you were looking at, for example, modifying a routing decision based on the density of an area, you can select the object type pedestrian routing decisions and pull out the relative flow of that pedestrian routing decision. And then you can use the lookup table to look at the density of an area and then navigate people accordingly. And then finally, the last set of attribute modifications that we have are these logs, where basically here we can see that lookup table. So we're looking at area measurement number 4, and we want to pull data off of the area number 143. So this is looking at the in-store area, so 143. So here we did a lookup table where we're pulling the area attribute distance violation seconds, and we're writing it to this distance violation seconds in the attribute modification right there. And so if we look at our area measurement results, We can see nearest neighbor risk outside, in store, things like that. Those are all being calculated. We can look at the area measurement list, and I think that's where they're actually storing the data, is in this list for various time intervals. I'll just scroll all the way to the end. Oh, it hasn't completed the simulation yet. So let me run the simulation all the way to the end real quick. But that's how you can use the nearest neighbor to analyze various situations. Okay, here we go. We can see that distance violation seconds outside, distance violation seconds outside for various time intervals, and inside and things like that. We just had to finish the simulation. But again, some of the user-defined attributes you can store data, or they can calculate data, and so you'll pair your user-defined attributes with formula-based routes and these attribute modifications to help navigate people through the network and track data as they go through. So for example, you can have an attribute modification that assigns a pedestrian a ticket number or a ticket gate, right? So if we're talking about an airport, they get dropped off, they go into the ticketing concourse, they approach a desk, and then anyone at a desk, you have an attribute modification, anyone at a desk gets assigned a terminal based on percentages or something like that. And then they would be routed based on the terminal that they're assigned. So, so that is the conclusion of that model.